Hi everyone. Today let's talk about non-constant coefficient second-order linear homogeneous equations. So last time we talked about second-order linear differential equations with constant coefficients. How about non-constant coefficients? Okay, so very few of the non-constant differential equations that we know how to solve. Okay, one class we know how to solve is called the Cauchy-Euler equations or equidimensional equations. Okay, so why do we call them equidimensional equations? That is because each term in an equation must have the same power of x as the order of the derivative. So you can see here is second order, so we have x squared as its coefficient. Here we have y prime, the first derivative, so we have x as its coefficient. And here we don't have a derivative, so we have the constant term as its coefficients. So equidimensional means the power of x is the same as the order of the derivative of that term. Okay, so how to solve? The trick is we're gonna use a substitution, okay? We let t be ln of x. Okay, so what happened? Okay, let me show it here. So if we change the variable, let t be ln of x, then dy dx is dy dt times dt dx. This is by the chain rule. Okay. And what is dt dx? Well, dt dx is the derivative of ln of x, which is 1 over x. So that's why here we have dy dt times 1 over x. And then how about the second derivative? So the second derivative is d dx of dy dx. Okay, which is the derivative of this part. Okay, so but this guy we have a product, so we need to use product rule. So it's the d dx of dy dt, and then the second guy plus the first guy times the derivative of the second guy, so d dx of 1 over x. Okay, so what is that? So you can see d dx of d dt, we can use chain rule again. That is d dt of dy dt, okay, and times dt dx, okay, times 1 over x plus dy dt. Derivative of 1 over x is actually negative 1 over x squared. Okay, but dt dx is also 1 over x. So that's why we get this is actually the second derivative of y with respect to t. And then here we have 1 over x squared plus dy dt times minus 1 over x squared. Okay, so we get dy dx and second derivative, and so we can then plug this into our original differential equations. Okay, so what do we get? All right. If we plug into the original differential equation, so let me use a different color. Okay, so let's plug in this guy and this guy here. So we have a x squared y double prime. That was the derivative with respect to x. That is the second derivative of y with respect to t. And then 1 over x squared plus dy dt times minus 1 over x squared plus bx times y prime. Y prime is dy dt times 1 over x plus cy equal to 0. Let's distribute it. Can you see all the square cancel? So we have a times the second derivative of y with respect to t. And then here we have minus a dy dt. Next, x cancel. So we have b dy dt plus c y equals to 0. Okay, and so what's next? So we have a dy second derivative, and then here we have, let's factor out dy dt, then we have b minus a plus c times y equal to 0. So that is our equation. Okay, so this is an ODE about t instead of x. So we have successfully changed the variable to t. And what is special now, you can see all the constants. So all the constants, this guy, and this guy, all constants are, so I mean all coefficients are constants. So all coefficients functions are constant. And then we can use the method we learned last time. Okay, last time we learned about how to solve second order ODE, linear ODE with constant coefficients. Okay, so and we know that the solution looks like a e to the rt, right? But remember, this is like e to the t to the r. And what is t? So t is ln of x. What happened? E and ln cancel. So we have a x to the r. So actually solution is of this form. Okay, so when we see the Cauchy-Euler equations, or what we call equidimensional equations, then the solutions is going to be of the form of ax to the r. Okay, so so suppose that is our solution, then we take the derivative of it. Okay, so we take the first derivative. We can see this is, we use power rule. The first derivative is a times r, and then the exponent becomes r minus 1. When we take the second derivative, we moved this down in front, so r times r minus 1, and then a times x to the r minus 2. Okay, so plug this into our differential equations. So our original differential equations. So y double prime is here. Okay, and then we plug in so a y double prime plus b y prime plus c y equal to 0. Now what happened? Can you see x squared and x to the r minus 2? They combine to x to the r. And here x and x to the r minus 1 combine to be x to the r. Here we have x to the r. So all the terms have x to the r. So let's factor out a x to the r. What's left? So here what's left? We have a r times r minus 1. And we have b r. And then we have c. So that's why this is what we get. And because a times x to the r is not 0, okay, for all x greater than 0 or for all x less than 0, then it force this factor must be 0. So this is our characteristic equation for the Cauchy-Euler equations. So this is the characteristic equation. Okay, so that means so in our last time, the characteristic equation, you just like a r squared plus b r plus c equal to 0. So this is for second order linear ODE with constant coefficients. Okay, but now this is for this is the characteristic equations for Cauchy-Euler equations. So let's compare the difference. Okay, so I would say I would suggest you to use this one instead of that one, even though they are the same, but actually this one show more pattern. Okay, so when we have like higher order, not only like second order, we might have third order, fourth order. The way how we think of is actually this guy. Okay. All right. So that means whenever you see second derivative, you put a and then you put r times r minus 1. Okay. When you see first derivative, you do br, and then when you see the constant y, you just put c there. Okay, so that is the characteristic equations. And then we make it into this form, okay, because we want to know the coefficient of r squared, the coefficient of r, and coefficient of c. So then when we solve, we can use the quadratic formula to solve the roots. Okay, and remember, now the solution is x to the r. The solution is not e to the rx. E to the rx is only for linear ODE with constant coefficients. Okay, but now our coefficients are now constant. So if you can remember, so we have the 3 cases: 2 distinct real roots, 1 repeated root, and 2 complex conjugate roots. Okay. All right. So what do we see? Okay. I also want to point out that this guy is actually the characteristic equation for this differential equation with constant coefficients. Okay, but the independent variable is t instead of x. Okay, so if we use this concept, we can write out our solution. Okay, so what do we have? We have a y prime prime, but let me make sure. So this is the second derivative with respect to t, and then we have b minus a dy dt plus c y equal to 0. And the characteristic equation is ar squared plus b minus ar plus c equal to 0. And depending on the discriminant, we're going to have 3 different roots. So if we have 2 real roots, what are the solutions? It's going to look like y equals to c1 e to the r1t plus c2 e to the r2t. But what happened? So you can group the t and e together, and that's e to the t to the r1 plus c2 e to the t to the r2. But what is t? Well, t is ln of x. So e to the t is actually e to the ln of x. That is x. That is why if we plug in x into like e to the t, we get this formula. Okay, so this is solution in x, in terms of x. For the repeated roots, r1, okay, our solution was like c1 e to the r1t plus c2t e to the r2t, right? But now e to the r1t is like x to the r1, and c2, t, what's t? ln of x. and e to the r2t is x to the r2. So that's why we get the new formula. This is our new formula. And for two complex conjugate roots, alpha plus or minus beta I. So if you can remember, our solution is C1 e to the alpha t, and then cosine beta t, plus C2 e to the alpha t sine beta t. Okay, so now we know we group the e and t together, so that's why we get C1 x to the alpha, and then cosine beta, but t is ln of x. And then we have C2 e to the t is x to the alpha, sine of beta, but t is ln of x. That's why we get this new formula. Okay. So for Cauchy-Euler equations, you just need to remember those three formula. Okay. All right. So let's see how do we solve the examples. So first example, find the general solution of this ODE. Okay, so this is the ODE with a Cauchy-Euler equation, right? This is x squared, this is x, this is the constant term. So in this case, a is like 1, b is like 3, c is like minus 3. And then we know our solution looks like a x to the r. What is the characteristic equation? The characteristic equation is AR squared plus B minus AR plus C equal to 0. So A is 1, B is 3 minus 1, R, C is negative 3 equal to 0. So R squared plus 2R minus 3 equal to 0. So how do we factor it? Plus 3 minus 1, right? So r equals to negative 3, r equals to 1. So we have two real roots. Okay, so if we have two real roots, what is the formula for it? So we use the first set of formula. So we have C1 x to the r1 plus C2 x to the 1, which is just x. Okay, so this is our solution. And because we don't have initial conditions, so we don't need to solve the constants, C1 and C2. All right, so that is example 1. How about example 2? So you can pause here and try to work on this problem. Are you done? So A is 1, B is negative 3, C is 4. Okay, and this is Cauchy-Euler equation solution looks like A x to the r. Then the characteristic equation is A r squared plus B minus A r plus C equal to 0. A is 1, B is negative 3, A is 1, C is 4. So we have minus 4r plus 4. Do you know what that is? Well, that actually is a complete square. Yes, that's like a complete square. So we have a repeated root 2. And why do we call it repeated? Because you see, the number of copy of this factor is 2, so it's repeated. And this copy is actually the multiplicity of that root. So the multiplicity is 2. So the multiplicity is the number of copies of the factor. Okay, so r equals to 2. Then what is the solution? Well, the formula for it is C1 x to the root plus C2, and then ln of x times x to the 2. So far, so good, everybody? All right. let's look at example 3. You can pause here and try to work on this problem first. So this is, see, x squared, x, and constants. We have Cauchy-Euler equation. So we're able to solve. A is 1, B is 7, C is 25. So A, B, C, they are constants, numbers. Okay? So we know the solution looks like ax to the r. And then the characteristic equation is ar squared plus, do you remember it? Do you know what that is? Next, is it br? B minus ar. Okay, that's the main difference. If we have linear ODE with constant coefficient, this is just b. But if we have Cauchy-Euler, then this is b minus ar. Okay, and then the first term and the last term are the same in both cases. So we have c equal to 0, a is 1, b is 7, c is 25. 6 plus 25 equals 0. Okay, so let's check. B squared, discriminant, b squared minus 4ac. Oops, of course, negative. So we know we gotta use quadratic formula. It's gonna be 2 complex roots. And the complex roots always show up as like a complex conjugate. Okay? So what's the quadratic formula? Okay, we have 2a, a is 1, so just 2 in the denominator. And then negative b plus or minus b squared, 36, minus 4ac is 100. Do you know what is 36 minus 100? Is negative 64. So negative 64, square root of 64 is 8. Square root of minus 1 is I. So this is the complex number come into play. Okay, square root of minus 1 is I. So we divide it by 2, we get negative 3 plus or minus 4i. And this is the real part. This is the imaginary part. Okay? Alright, so what is our formula? Our formula is C1, x to the alpha. Alpha is negative 3. And cosine beta. Beta is 4. ln of x plus C2, x to the minus 3. Sine 4 ln of x. So you can see cosine and sine always come together. They're like a pairs, like a couple. Alright, so that is example 3. So example 4 is like a challenge problem. Okay? You can see the degree here. We have a third order differential equation. So if we have a third order differential equation, what are we going to do? Alright. So we know this is the Cauchy-Euler equation, right? So our solution looks like a times x to the r. So y prime is then ar x to the r minus 1. Y prime prime is ar r minus 1 x to the r minus 2. Y prime prime prime. Okay, the third derivative is then ar r minus 1 r minus 2 to the r minus to the so times x to the r minus 3. Right? Okay, so we're gonna put this into our formula. So x cubed y triple prime is ar r minus 1 r minus 2 x to the r minus 3. Okay, And then we have x squared y prime. So double prime r minus 1 x to the r minus 2. And then x, so x, where is x? X, y prime is ar x to the r minus 1. That equal to 0. So you can see when we combine all the x, all the terms have a x to the r. So we factor it. What do we get? We get r minus 1, r minus 2, minus r minus 1. Okay. And next we have r. So far so good. So this is to our problem. So actually we can summarize in general. Okay, if it's third order ODE with the Cauchy-Euler equations. Okay, so we're given a x cubed y double prime b x squared y double prime and c x y prime and d equal to 0. Then the characteristic equation is gonna be a, then the highest power is like a times r minus 1 and times r minus 2. Okay, and plus b times r minus 1. Okay, and c times r. So you always start with r and then you like count down. Okay, and the end d equal to 0. So this is in general our characteristic equation. So that's why when I first introduced the Cauchy-Euler equations, I say it's more general to look at this one instead of this one. Okay, so this is why when you have higher term, you just have more terms like r times r minus 1 times r minus 2. So if you have a fourth order, you can imagine the next one in front of it should be r minus 1, r minus 2, and r minus 3. So when you keep increasing the order, it's just like multiplying more factors, okay, of r minus a number. So you just count down. Okay, all right, so let's go back to our problem. Okay, so let's figure out so our characteristic equation. So let's multiply it out. We have r, so r minus 1 times r minus 2 is r squared minus 3r plus 2 minus, we distribute the r, so we have minus r squared plus r is 0. So far so good. Oh, can you see we have a common factor r? So our goal is to factor it completely and then find the root. Okay, so because we already seen all the terms have the r, let's factor that out. Here we have the r, and here we can combine them is like 2r. We factor out the r, we get 2. So we have r squared minus 4r plus 4 equal to 0. Okay, and we can see that is a complete square. And this is how we can factor. And what are the roots? Well, the roots, this corresponds to r equal to 0. This corresponds to r equal to 2. But because the multiplicity is 2, we know this is the repeated roots with multiplicity is 2. The multiplicity actually plays an important role, okay, especially in the higher order ODE. So in the next session, when we talk about higher order ODE, we're gonna look carefully the multiplicity of each root. Okay, so what is our final solution? So this guy corresponds to C1, x to the 0, right? X to the 0, that is 1. So that's why the first term of our general solution is just the constant C1. And then we have C2. This guy corresponds to, let me use a different color. Okay, so this guy actually corresponds to 2 terms. Okay, if you see this factor is 2, it actually correspond to 2 degrees of freedom, C2 and C3. So C2, x to the 2, because it's repeated, what happened with repeated? You have an extra factor of ln of x. Yes, that's the extra factor of ln of x. So this is our solution of this problem. Okay? Yes. So next sessions, when we go over the higher order ODE, you'll see more example of like this theories about like more rules and more multiplicity. Okay? All right. See you in the next session.